let's get started.
I'm scared to leave.
Okay, so last week, what did we do? Isomorphisms?
Yeah.
But we're still just talking about groups. I don't know, we need to refresh on isomorphism, but let's at least refresh on group. What is a group? A set together with an
Operation.
What's an operation? What's an operation on the set A?
Takes two and gives out one.
It goes from A cross A to A. Oh yeah.
Its domain is A cross A. We say nothing about its range or codomain.
Oh, okay.
An operation is a function whose domain is A cross A. That's an operation on A. It's closed if its output is also in A. Right? So a group is some set together with an operation on that set, such that one, the operation is closed. Right?
Yeah.
What else?
There's an identity element. There's an identity.
There's an identity element. The operation is associative.
And then each element has an inverse.
Every element has an inverse element also in the group. That make sense?
Mm-hmm.
Can we go over the inverse element again?
Yeah. Give me a set.
Z to the 12.
Z12 like that?
Yeah.
Okay. So if you give me Z12, then we'll use the plus operation.
Okay.
Now give me an element in Z12.
5.
5. So 5 plus 5's inverse has to give me the identity. What's the identity for this operation?
0.
0. So what is the magical number such that when I add 5 to it, I get the identity?
7.
7. So
Wait.
7 is 5's inverse, so 7 better also be in there since this is a group.
But what about sets that isn't Z12 or stuff like infinite sets? Like just Z. Could you still do it?
Sure. So you want just Z. Now the group that we'll use on Z, there's an operation we can put with it. That operation is plus.
Okay.
Give me any integer.
8.
8. 8 plus 8 inverse is equal to 0. What's 8 inverse? Negative 8. That's how we define our negative numbers. They're the additive inverse of negative A is the additive inverse of A by definition. That's one way of defining negative numbers.
Wouldn't they
Okay.
all have an inverse?
Yes, that's what we're demonstrating.
Oh.
In a group, every element has an inverse. Yep. So we were just looking at examples until it appealed to his intuition. So we're good?
Yeah.
Okay. So that's what a group was. Now, what was an isomorphism?
Oh, it was
So if I have two groups, G and H,
it was a way of saying that they're somehow the same.
That means it's both 1 to 1 onto.
so F is a function
Oh yeah.
from G to H such that F is a bijection and what?
F of A dot B is equal to F of A star F of B.
Perfect. That is exactly right. So it's a bijection that preserves the group structure. That's another way that we say it. Same way that a homeomorphism is a bijection that preserves continuity. This is a bijection that preserves the operation.
Okay.
Wonderful. So, that's a good recap. Now we're ready to get into today. Today, the topic's pretty simple. Some of these proofs might seem a little bit weird, and we're going to introduce an operation that you're going to find very strange. But the main topic that we're talking about today is a subgroup. And a subgroup is almost exactly what you would have guessed, but here's the definition. Let G dot be a group, and let H be a subset of G. If H dot is also a group, then we call it a subgroup. So here's a group, pick a subset of G, namely H, If H together with that operation is also a group, then we call H with that operation a subgroup of G with that operation.
Right.
Make sense?
Isn't that kind of like a subspace in topology?
Kind of. The topology actually changes when you take a subspace. Because you have to take all the open sets and intersect them with the set that you're defining the topology on. So not quite, but it's close.
Okay.
Anyways, subgroup. So let's look at a group really quick, a nice, easy, small group, and let's look at a bunch of its subgroups. And let's make sense of why it doesn't have any other subgroups. So looking at Z10, we remember what Z10 is, right? How many elements are in Z10? What's the biggest thing in there?
9.
What's the smallest thing in there?
0.
Wonderful. And then regular modular arithmetic addition. So I'm saying that H equal to this, H equal to this, H equal to this, and H equal to this are all the possible subgroups. So H with just 0 and plus is going to be a subgroup of this. H equal to the set itself is obviously, the set is a subset of itself. This is Z10, right?
Yeah.
Is Z10 a subset of Z10?
Yes.
So a group is always a subgroup of itself.
Yes.
Is
Yeah.
0 always a subgroup of the set?
The set containing just the identity element is always a subgroup. That, together with the operation, is always a subgroup of G dot, where this is the identity element in G.
That makes sense.
In this special case, it happened to be 0. If we were doing Z star, it would have been 1.
What's Z star?
Z star is all the ones, so we have an example right here, so we'll just jump ahead for a second just to see a set. So Z25 star is all the elements in Z sub 25, there's 25 of those, right? 0 through 24. It's all the elements in there that are relatively prime with 25.
Oh, yeah.
So for example, 5 is not in here,
Because 5 times 5.
because 5 and 25, their GCD is 5, not 1. But 2 is in there because the GCD of 2 and 25 is 1. Make sense?
Yes.
All right. So here's a group, and I'm saying H equal to these 4 sets are all the possible subgroups, and they are, first of all, subgroups. So first off, let's validate to ourselves that if I let H be any one of these, it is a subgroup. What do we require for it to be a group?
Close.
Closed. All right, so let's look at this one. If I take 0 and I add it with 0, do I get something in this set? Yep. So this one's closed. What about this one? Is this one closed?
Yeah.
Yeah, that one's trivial. What about this one? Is it closed?
Yeah.
0 plus 5 is 5, that's in there. 5 plus 5 is 0, that's in there.
Okay.
0 plus 0 is 0, that's in there. It's closed. And then this one, 0, 2, 4, 6, 8. Is that closed?
Yeah.
Yeah. An even plus an even, mod by 10, is going to be one of the evens, mod 10. So now, I'm saying that these are all the possible subgroups. Oh wait, that was just closed. We can't just say closed. So we got closed, what else do we need to check?
Associative.
Associative. Since the group is associative, then obviously the subgroup is associative, and we don't even need to prove that. If this operation is associative with this group, this operation is associative with the subgroup.
Okay.
It's associative with everything in there. A subgroup only has things in there. Therefore, it's associative with everything in a subgroup. So associativity, when you're dealing with a subgroup, isn't something you need to validate to make sure it is a subgroup. If you knew that your initial thing was a group, then your subgroup automatically, whatever you're trying to check to see if it's a subgroup, you get associativity for free. That's what I'm trying to say. That make sense? Okay, what else do we need to check? Identity. Does that have 0? Does that have 0? Does that have 0? Does that have 0? Okay. What else do we need to check? Inverses. What's the inverse of 0? 0. So that one has all its inverses. Obviously, the inverses are going to be just elements of the set since this was already a group, so we don't need to check that one. This, does it contain its inverse?
No.
What's the inverse of 5? 5. What's the magical number I can add to 5 to get the identity element? 5. What about this one? Well, 0's inverse is 0, so we got that. What's 2's inverse? 8, that's in there. What's 4's inverse? 6. So we have all their inverses in there as well. Okay, so these are all subgroups.
No, you just proved they're a group, right?
Well, they're subsets of the
They're
set.
subsets of this.
Then they're all groups.
So I'm saying do this set with that operation, it's a subgroup of this. Do this set with that operation, it's a subgroup of this. Do this set with that operation, it's a subgroup of this. Do this set with that operation, it's a subgroup of this.
So how do you prove something's a subgroup? Just do that? Just
We
prove
just
that
did
it's a
it.
group?
You just need to validate those 3 properties.
Yeah.
1 is H a subset of your initial set G? Yes, 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 yes.
Okay.
Okay, next, is it associative? Yep. Does it have the identity? Yep. Does it have its inverse? Yep. What am I
Is it
missing?
closed?
Is it closed? Yep. And we're done.
Okay.
And in general, you just need to prove the 3. You don't need to prove associativity, you just need to prove the identities in there. You need to prove it's closed, and you need to prove the inverse in there. And usually just proving it's closed and that the inverse is in there is the hard part, because that's just pretty easy.
How do you know that that's all of the subgroups?
Wonderful. How do we know that this is all of the subgroups? Well, first off, let's say, what if 1 is in H? What does that imply? So we're saying that these are all the possible values for H, right?
Yeah.
Okay. So let's say, what happens if we allow 1 to be in H?
Then 9 has to be in there.
What else do we know has to be in there?
9.
9 has to be in there. What else?
0.
What else? If 1's in there, does 1 plus 1 have to be in there?
Yes.
So 2 has to be in there. Does 2 plus 1 have to be in there?
No. 9.
It has to be closed under addition.
Then how is that?
Wait.
0, 2, 4, 6, 8 closed.
This one?
Yeah.
Pick any 2 elements in here.
2,
And
6.
what's 2 plus 6? It's in there. Pick 2 more. Should we do 8 plus 6? What's that?
Yeah, but you can do 3 instead of 1.
3 isn't in there.
I'm saying, it's like,
Oh, well, we're just going to do one at a time. I'm going to say, look, if 1's in there, look what has to be the case.
yeah.
If 3's in there, look what has to be the case, etc.
Wait, what does closed mean?
Closed means that when you add it together, you get an element in the set.
Okay, but so why if 1's in there would you add 1 to 1?
So let's say I know that 1 is in H. That means that 1 plus 1 has to be in H. Because this operation has to be closed on H, if H is a subgroup. One of the properties of being a group is that you're closed on your operation.
You don't have to.
So this has to
Why
be
do
in
you
H.
add it
You don't have to add it to
yourself?
itself. You can add it to 9.
You can pick any 2 elements.
Okay, then add
Is
it.
1 in H?
Any 2 elements in the original set.
No, in H.
But
You can add it to 9.
I said if 1 is in H, what else do we know is in H? So you have no clue what H I chose.
Okay.
I've got some H, and all I'm telling you is that H plus is a subgroup of this. Okay, that's all you know.
Okay.
Now I give you more information. I tell you 1's in H. Now what do you know?
0, 1, and 9.
You know that 2's in H. Because this is a group. Which means it is closed under this operation. Which means if I take an element in there, and I apply that operation with another element in there, pick any 2 elements out there I want, apply that operation, I better get an element in there.
Oh.
Pick 2 elements in here, namely 1 and 1, doesn't matter if they're the same. Apply the operation. Whatever comes out has to be in there, otherwise the operation is not closed. That makes sense? So 2 has to be in there. And if 2 has to be in there,
3 has
3. And if 3,
4,
and then,
5,
and then,
7, 8, 9.
exactly. So if 1's in there, then we instantly know H is equal to this set, Z10. Right?
Yeah.
What about if 3's in there?
And 6 has to be in there. 3, 6, and 9.
3, 6, 9, 2, 5, 8, 1, 4, 7.
Why?
I was just adding 3. I'm counting by 3. What's 3 plus 3?
It just restarts.
Just do the math. What's 3 plus 3? Plus 3.
9,
Plus 3.
2,
Plus 3.
5,
Plus 3.
8.
Plus 3.
What?
Plus 3.
3?
Plus 3.
7.
You just said all the numbers except for 0. So plus 3 one more time.
0.
0. Okay. So if 3's in there, h has to be z10.
Oh my gosh.
Right? What about if 7's in there?
2.
Well, if 7's in there, what's the inverse of 7? 3's in there. Which gives us h is equal to z10. Because that's its inverse, right?
Oh. Yeah.
Let's see, what else? What happens if 9's in there?
And 1's in there, and then
Then 1's in there. Perfect. Which gives us h is equal to z10.
So how do you get the other ones?
Well, notice that the other ones could pop up in different ways. If 2's in there, I was just doing all the ones that instantly give us z10. 0 is always in there, so 0 doesn't give us any new information. What happens if 2's in there?
4, 6, 8.
Then the evens are in there,
Yeah.
right? If 4's in there, what does that give us? 4's in there gives us 4 plus 4 plus 4 is in there, which is 2. Which gives us all the evens. Same thing with 6, same thing with 8. And then 0 gives us no new information. And then finally, if 5's in there, what do we know? 0's in there. Right? So now we look at all the possible combinations we can have with having so this limits what they could possibly be, right? So I can either have z10, 0 by itself, or the evens, or 0 and 5. And we just went through all the possible cases for this group. The only one that is questionable now is why can't we have 0, 5, and the evens? And the reason we can't have that is because then 5 plus 2 is 7 isn't in there. So that's how we rule that one out. So this is kind of a messy process of finding all the subgroups. But mostly this was just to get you comfortable with what a subgroup is. Feel good? Alright. Then let's look at another example now. S3. This is your guys' favorite set. S3. What's S3? With composition, obviously. Obviously,
Alright.
you can only compose permutations together.
Oh.
So what's S3?
Permutation.
Good. Close. S3 is all the possible permutations you can create on the set 0, 1, 2 on Z sub 3. You remember permutations? You remember what a function is?
Yeah.
Yeah? Kinda? Alright. So we got a set 0, 1, 2. The first 3 natural numbers. Now you know what a function is. So now imagine a function from this set to this set.
Right.
You with me? We map all 3 of those elements to these elements again. A function. From this set to this set. Now we require that the function is 1-to-1 and on-to. Or in other words, we require the function to be a bijection. That's a permutation on this set. S3 is a set of all permutations you can create on this set. Question, how big is S3?
Well, it says 6 right there.
Well, why is it 6?
Because it has 6 elements.
Yeah, those three possibilities with first and then 2 and
Perfect. Because 3 factorial is 6. The function has to look like it has to take 0, map it to something. It has to take 1, map it to something. It has to take 2, map it to something. And that's it, right? So we have 3 options on what 0 can map to. It can map to 0, 1, or 2. But now, whatever we use, if we use 1, we can't map 1-to-1 now. Otherwise, the function won't be 1-to-1. So now we only have 2 options on what we can map 1 to. We can either map to that or that. So we have two options for what we can map that to, and then how many options do we have for the two? 1. So question, how many permutations are in S sub 5? 5 factorial. That easy. Okay. So S sub 3, all the permutations on the set 1, 2, 3, or 0, 1, 2, or 1, 2, 3, doesn't matter how you think about it. All the permutations you can create on some 3 element set. Huh? And then composition. You remember what this is?
Kind of.
Yeah.
Kind of. It's how you combine functions. It's doing multiple functions in one. One function maps A to B, another function maps B to C. Compose them together, you map A to C.
Yeah.
Right? Composition. Okay. So if you take a permutation and you compose it with a permutation, you get out a permutation. A bijection composed with a bijection is a bijection. Good? When they're defined on the same sentence. Okay. Now we had a special notation, iota, which was the identity permutation. Oh boy, you probably don't remember how to read cyclic notation then, huh?
No.
1 goes to 1, 2 goes to 2, 3 goes to 3. If we were looking at this one says 1 goes to 2, 2 goes to 3, 3 goes to 1.
Yeah.
Shorthand for writing a permutation.
Yeah.
Alright, you remember that now?
Yeah.
Okay, so if 1 goes to 1, 2 goes to 2, 3 goes to 3, that's the identity permutation. And we use iota to signify the identity permutation. Alright?
Okay.
So we're looking at S3, there's 6 elements in there. One of them is obviously iota, that's its identity element. And this thing is a group. We already showed that permutations composed with permutations gives you permutations. So we know it's closed. It has an identity element, that's in there. The inverse, that's also something we proved back when we did these, that the inverse of a permutation is still a permutation. And what else are we missing?
Associative.
Associative. We also proved that function composition is associative and not commutative. It's just associative. So hopefully that rings some bells, brings you back a little bit. If that doesn't, my final will for sure. So the final that you're going to take, you know.
What is that?
When is that? That's on the last day of school. And it's 50% of your second semester grade.
That doesn't include permutations.
50%?
Yes, it does.
We did that in the second semester.
It includes everything.
Dude, the final is the final, not the midterm.
You
Final
said
includes
we only
everything.
did final with the second semester.
It could. Who knows? We'll have to see what I wrote.
Scared.
You better be. Go reread the whole book. You still won't be prepared. So read it twice and then you'll be fine.
I actually don't think I would.
If you really read it, I don't mean just say the words out loud. I mean read it, all the arguments. Yeah, you do that twice, you'll be fine.
It's gonna make me cry.
That's okay. Alright. So, let's look at some subgroups on this thing. And we'll try to make sense out of a couple of them, I guess, but not too many. Obviously, the set containing just the identity element is a subgroup, right? Let's look at this one. We have 2 permutations in here. The identity permutation and this permutation. This permutation maps 1 to 2. It maps 2 to 1. And it maps 3 to 3. Right? This permutation is the inverse of itself. You run this permutation once, it swaps 1 and 2. You run it again, it swaps them back. It undoes itself.
Okay, wait. Are you saying all these are subgroups of that group?
Yes.
But doesn't that group only have?
This has 6 things in it. And they're right here.
Why do they all need identity?
Why do they have more?
They're groups.
Oh,
I'm confused how this works. Why do they have more than one permutation?
Oh, sorry. It's right here. This is all 6 of them. Have more than one permutation? They have
Oh,
6
okay.
permutations.
Okay.
This is a set of 6 functions. The first function is just the identity. The second function maps 1 to 2, 2 to 1, and 3 to 3. This function maps 1 to 3, 3 to 1, and 2 to 2. This maps 1 to 1, 2 to 3, 3 to 2.
So if you're saying that those are subgroups, what are you saying about it? How does composition go into it?
We already proved that composition is the operation.
Yeah, so what are you saying about the subgroups with composition?
Here's the set, here's the operation. This set with this operation is still a group. Let's pick one and just work it through all the way. Let's work it through all the way. I don't care which one we pick. Do you care which one we pick? You okay with just doing that one since it's close to me? Let's look at this one and validate that it is a group, and let's do all the work to just make sure completely. Well, this is the first thing we need to validate.
It has the identity.
It has, or it's a closed operation. Okay, we can start with the closed operation. I composed with I, the identity function composed with the identity function is just the identity function, right? So let's look at this one. Let's apply this function. I know that the identity applied to this just gives me back this, and this applied with the identity just gives me back this. Let's apply this one with itself and see what we get. Okay? Now, just to be super clear, I'm going to write this function out explicitly so that there's no confusion about what exactly this function here is doing. It's mapping 1 to 2, it's mapping 2 to 1, and it's mapping 3 to 3. Here's the function explicitly, right? Now I'm going to apply this function twice. I'm going to take to this function, and I'm going to compose it to itself, and see what we get. You with me? So let's see what we get when I compose this with itself. So if we call this pi is equal to that, then pi composed with pi is equal to, and that's what we're figuring out. Okay, so let's see. We're going to start with 1. What does 1 go to? Well, when I run function, when I do this one, we get 1 goes to 2, right? Now I need to apply, well, actually you apply it this way first. So pi takes 1 and maps it to 2, and then this pi takes that 2 and maps it to 1, so it went back to 1. You with me on that? 2, apply to the first pi, 2 goes to 1, then apply 1 to this one, 1 goes to 2, so 2 goes back to 2, and then obviously 3 just goes to 3. So it gives me back the identity, which is in there. Does that make sense?
Yeah.
Now notice how pi composed with pi gave me back the identity element. Another thing that tells me then is that pi is equal to pi inverse. It's its own inverse. When I apply it to itself, I get the identity. Right? So it's in there. Now its inverse is also in there. The identity's inverse is in there. Obviously that's just the identity. It's closed. What else do we need to validate? Associative. And we know it's associative because we know function composition on permutations is associative. That make sense?
Yeah.
Okay. And doing this one's almost going to be no different. In fact, it's probably pretty obvious to you that this is going to be isomorphic to this, is going to be isomorphic to this. It's just a relabeling. Here's the third one, and then finally our whole group. Something to notice about all these groups is, what's the size of this one? What's the size of this one? 1, 2, 3, and 6. What do all those numbers have in common? They all divide 6. They're all divisors of 6. So, let's come back up here and look at this one and look at the same thing. What's the size of this?
1, 10, 2, 5.
So up here we had 1, 2, 10, 5. 1, 2, 5, 10. Down here we had 1, 2, 3, 6. All those happen to divide the size of this. So all these together divided 10, and all these together divided 6. The natural question is, does the size of a subgroup have to be a divisor of the size of the group?
Yes.
It always has to be?
Probably.
Yeah, probably.
I think so.
Well, we're going to prove it, and then you won't just think so, you'll know so.
So how would you go about finding those subgroups? Same way we did down there.
Would you first do all
It's not always trivial coming up with what all the subgroups are, and I don't have any systematic way for you to just know. So, I mean, if you were coming up with these on your own, probably write down the permutations, write down their inverses, and then just start playing with it. I don't know, I don't have any good method. And similar types of thinking, like if I allow this permutation to be in there, what else does that require? And you start composing it with itself, see the permutations that come out. That's the most systematic way I can think of to just know how to do that. But there might be some good, clever way that I don't know. Okay, let's see. So now we're on to our next definition. Okay, the definition that's going to be the hardest thing for you to swallow in this class. So let G dot be a group, and let H dot be a subgroup, and let little a, little b be elements in G. We say that A is congruent to B mod H, provided that A dot B's inverse is in H. And we write A is congruent to B mod H. This has nothing to do with mod how we were using it before. This is a completely
Yeah, we've done that 3 different times.
This is a completely different thing now. This is not talking about modular arithmetic. This is not saying that H divides A minus B. All this is saying is that this is saying this. If A is congruent to B mod H, that means A dot B's inverse is in H. Very strange. There's no reason that you should look at that and say, oh, that's easy to work with. Ready to continue? Well, we're just writing. Okay. So let's look at an example to try and wrap our heads around what on earth this thing is saying. So the example we're going to look at is Z25 star and multiplication. And the subgroup that we're going to use, H, is 1, 7, 18, 24. And I'm just telling you right now that that's a subgroup. We'll validate it here with the table in a second. I want to write out Z star 25 in case you forgot what on earth that means. So notice how we're missing 5, 10, 15, 20, 25. Well, 25 would have been in there anyways. Oh, and 0. So this has 20 elements in it. It's missing 0, 5, 10, 15, 20.
0 can never be in height in the starting.
Correct. Okay. So you know what group we're working with, and we're talking about this subgroup. Now let's really quick validate that this is a subgroup. The easiest way to do that is to just write out a multiplication table for it. So 1, 7, 18, 24, 1, 7, 18, 24. We're going to validate really quick that it's closed. So notice that when you do this multiplication table, all the numbers that you get out of it are elements in H. Second, notice that the inverse is in there. What's 1's inverse? 1. What's 7's inverse? 18. What's 18's inverse? 7. What's 24's inverse? 24. So it contains all the inverses. So it's closed, contains all the inverses. Associativity, we already know multiplication's associative, so we don't need to worry about proving that. And then, what's the other one? Identity. 1's in there. Okay. And notice 1 is an identity. 1 times 1 gives 1, 1 times 7 gives 7, 1 times 18 gives 18, 24, similarly 1, 7, 18, 24. Okay, so we validated everything. So H is closed, 1's in there, and H contains all the inverses. So it is for sure a subgroup. Now, the really weird, awkward part is 2 congruent to 3 mod H. What? Now to save this on the algebra, I already wrote down the inverse of 3. Remember, 2 is congruent to 3 mod H, means that 2 times 3 inverse is in H. So is 2 congruent to 3? What do we check? We check if 2 times.
Okay, wait, are they talking about 2 and 3 in Z25 star?
Yes.
Yeah. Okay. I was like, 2 and 3 are in H.
I'm going to put that up here. 3 inverse is equal to 17. Okay. So this is true. This is true if and only if 2 dot 3, oh, we're not doing dot, we have an actual group, so times. 2 times 3 inverse is in H.
Which is 7.
That's another way of asking the same question. I already calculated 3 inverse for you, so that's the same thing as 2 times 17 is in H. What's 2 times 17? 34, but mod 25? 9. Is 9 in there?
Yeah.
No.
No. Yeah, it is.
In H?
Is 9 in H?
Oh, in H.
No.
No.
No. So 2 is not congruent to 3 mod H.
Okay.
Feel like you got it?
Yeah.
It's really weird, but let's try another one. 11 inverse is 16.
How are you getting that?
I had it written down beforehand, so that we didn't have to go through the work of trying to come up with it.
You just have to find what the mod
11 times what mod 25 is equal to 1.
Okay.
That's how you can ultimately find it.
So 25 minus 11?
Huh? No. What's 11 times 16? Now we're going to do it. It's not that hard. What is 10 times 16?
160.
Add 16.
176.
176. Notice that 176 is one more than 175, which is a multiple of 25. So when you divide by 25, you're going to have a remainder of 1. So in Z25 star, the inverse of 11 is 16. See? It's not that hard.
Do we get to do
Of course, you're the
this
one who
mod
said
H stuff
that.
in our homework?
Over 25 minus 11.
Uh,
Right.
It will either be on your homework or on the test or possibly nowhere.
So it's one more than what?
I have no clue is the answer to that question. I picked out your homework forever ago. I picked out your test problems forever ago, and I haven't looked down since I've done it. So I have no memory. Anyways, so let's do the calculation. So this is the same thing as asking, is 2 times 16 in H? What's 2 times 16?
32.
Mod 25,
7.
7. Is 7 in H?
Yes.
Yes. So 2 is congruent to 11 mod H. Easy.
Okay.
Very unintuitive. You're just being told, look, here's an operation, here's how it works, use it. I have no way to make this appeal to your intuition. You just got to use it. But it turns out that this thing is a congruence relation.
What does it mean for it to be a congruence relation again?
Wow. What is a congruence relation? Not congruence relation.
An
See, I said the wrong
equivalence
word.
relation.
No wonder you're confused. Equivalence relation.
Okay.
This is an equivalence relation. Okay, we know what an equivalence relation is, right?
Yeah. Symmetric reflexive.
Hey, wait, Rhoda.
Yeah.
What is it?
Symmetric reflexive transition.
God. Okay. So, is that what we're doing next? Yeah, that is what we're doing next. So we're going to prove that this thing is an equivalence relation. Equivalence. Yeah, don't let me say the wrong word. Because I always say congruence and equivalence. I always mix those up. So let's prove it. So let H dot be a subgroup of G dot. Then we're going to prove that this congruent mod H is an equivalence relation on G. That's what we're proving. Alright, first thing we need to prove is it's
Reflexive.
reflexive. No, we already know that this is a subgroup of this.
Yes.
So groups are groups. That's proven. Next, we need to prove it's reflexive. What does it mean for it to be reflexive? We need to show that for any element in G you pick, G is congruent to G mod H. That's what we need to prove. So, what is G dot G inverse? just the identity, right?
Yeah.
Is the identity in H?
Yeah.
How do you know?
That's a group.
Because it's a group. Wonderful. So, G is congruent to G mod H. Because G dot G is in H. G is congruent to G mod H if and only if G dot G inverse is in H. This thing dotted with that thing's inverse is in H. Is the same thing as their congruent mod H. Yep, really weird to work with, but once you get comfortable, then it's not too bad. Okay, so everyone understands that this is reflexive and that's something you can do on the test.
Yes. Yep.
So,
If Rhoda can do it, you can all do it, right? And she said yes
For the most part.
for the most part. Okay, so you guys do the rest of it. She'll do most of it. You guys just finish.
awesome.
Next, we need to prove it's symmetric. So we assume that A is congruent to B mod H. We need to use that to prove that B is congruent to A mod H. And then it's symmetric, right?
Okay.
So assume A is congruent to B mod H. What does that mean? That means A dot B inverse is in H.
Yeah.
That's the definition of this, right?
Mm-hmm.
Now, since A dot B inverse is in H, A dot B inverse is in H because H contains all its inverse elements, right? It's a group.
Okay.
So if that's in there, its inverse is in there. You with me so far? So I know that this thing is in H. It turns out that that is going to be the same thing as B congruent to A. And we're going to show that. So A dot B inverse is in H. Alright, so now let's just show something really quick. Observe that A dot B inverse is right here. Notice that we're using that again. But look at B dot A inverse dotted with A dot B inverse. So this thing dotted with what we had up here. With me so far? So we're observing, what is this going to equal? Well, when we do this, it's associative, so we can rewrite our parentheses however we want. We rewrite it like that. What's A dot A inverse? The identity, right? So now we have B dot identity dot B inverse, which is just B dot B inverse, which is the identity, which is equal to the identity. Everyone follow the math there?
Yeah.
Now what we just showed is that this then is the inverse of this.
Yeah.
Because when we dotted them together, we got identity. So this is the inverse of this. So this is this. This and this are the same thing. That's what we just showed. Everyone see that?
Yeah.
Okay.
Okay. So we know that, since we know that this is in H, we now know that this thing is in H. Right?
Yeah.
So then, this thing is in H, which gives me that B is congruent to A mod H, which is what we were after. You follow that?
That was proof. What? That was
If I know that A is congruent to B implies B is congruent to A, we call that symmetric. Perfect. So now, we need to prove it's transitive. So now, assume that A is congruent to B and B is congruent to C. We need to show that A is congruent to C, right? Well, if A is congruent to B, what does that mean? That means A dot B inverse is in H, right? And since B is congruent to C, that means B dot C inverse is in H, right?
Yeah.
Now H is closed, which means if I pick two elements out of there and I dot them together, I get something in there, right?
Yeah.
So if I dot this with this, I get something in H. So that dot that has to be in H. Now just do the algebra. The B's cancel out. So I'm doing the algebra here. So take that, we're just doing the algebra. The B's are going to cancel out, well, regroup so we have the B's. that gives us identities, and we're just left with A dot C. So A dot C is in H, which gives me A squared C mod H. Did I go too fast?
No,
You understood
just
that?
fine.
Wonderful. See, this isn't that hard to work with. This mod H.
It's just weird.
I feel like it's gonna give us some massive proof.
Yeah.
Okay. So let's go back and do some example. Oh, well, what did we just prove? We proved that this thing is an equivalent relation. And equivalent relations give us equivalent
Classes.
classes. Feels like we just had this conversation last night. No way. So, equivalence relations give us equivalence classes. So now with this equivalence relation, I can divide G up into its equivalence classes. So let's do that real quick. So back to this same example. Here's my G. Here's my H. You with me?
Yeah.
I'm going to find the equivalence classes.
Okay.
What are all the equivalence classes of 1? Or, sorry, not all the equivalence classes. What is the equivalence class containing 1? It's all these elements.
How do you know that?
You would have to validate it. Now, this one right here is just H.
Yeah.
So the one containing the identity element is always going to be H. But let's maybe start with 2 for a second. So we already showed that 2 is congruent to 11 mod H, right?
Yeah.
So 2 and 11 have to be in the same equivalence class, right? And if we were to work out the algebra replacing 11 with 14, doing it already how you know how, right?
You have to there's a number, but I thought you have to do it. Yeah.
I'm not going to make you find these things.
Okay.
I'm just giving you an example so that you can see what they are.
Thank you.
With the equivalence classes though, then it doesn't matter what number is in there because they're all in the same group, right?
Yeah, I could have just as easily called this 7th equivalence class.
Okay.
And I could have put a 19 here. This is just a representative element. We're saying everything related to 19. These are everything related to 19. Because everything...
Anything in that would be congruent to each other mod H.
Yes,
Okay.
they're all congruent to each other mod H. And it gives us a partition on Z25, right? And notice that each of those parts is the same size. So this divides G up into 5 equivalence classes, all with size 4. In this case, 4 happen to be the size of H. Since H had 4 elements, we divide it up into equivalence classes of 4, size 4. Now, one thing to note, so I already said, notice that the equivalence class containing 1 is equal to H. And in general, the equivalence class containing the identity element is going to be your subgroup. And we'll do a quick proof of that. It's just a quick little one-liner, so we'll prove that H and the equivalence class containing the identity element are the same thing. So let's assume that you know that A is in the equivalence class containing the identity element. What does that mean? That means A is congruent to E mod H, right?
Yeah.
What does that mean? That means A dotted with E inverse is an H. What's the inverse of the identity element? The identity element. What's A dotted with the identity element? A. So if A dotted with the identity inverse is an H, then A is an H. So A being in H is logically equivalent to A being in the identity element's equivalence class. Notice that those are back and forth arrows. You can read this proof whichever way you want. If I know that A is in H, I know that this is true, I know that this is true, I know that this is true. Or you can read it this way. Doesn't matter. Okay with me?
Yes.
So, it's always going to be the case that one of your equivalence classes is just H. Good?
Yes.
Alright. Now, the lemma that I was in the middle of when I stopped. So, let's finish up this proof. So, let H dot be a finite subgroup of G dot. Then any 2 equivalence classes have the same size. So now I'm going to prove that any equivalence classes you choose are always going to have the same size. How am I going to do that? I'm going to pick a random equivalence class and so show it's the same size as H. Therefore, every equivalence class is the same size as H, therefore they're all the same size. So I'm going to pick a random equivalence class, show it's the same size as H, therefore every equivalence class is the same size as H, therefore they're all the same size.
Okay.
That clicking?
Yeah.
Alright, so then A2, we're showing, that's what we're showing. Okay, so let little g be anything in big G. And we're going to talk about its equivalence class, and we're going to prove it's the same size as H. And it remains to show that the size, you remember that notation for the size of the equivalence class containing G, notice that that's a set, is equal to the size of H. H is a set. Good so far? Okay. How do we show that two sets are the same size?
So that everything one, well, wouldn't you show that every, well,
How do you show that sets are isomorphic? Have we not ever talked about that?
We did.
Find an isomorphism.
Isomorphic in the set version of isomorphic. So when we get isomorphisms for groups, then the textbook says groups, in parentheses, isomorphisms, so you don't get confused with set isomorphisms.
I don't remember
How do we show that two sets are the same size, have the same cardinality? Okay, let's go back to how do I show that two groups are isomorphic?
Find an isomorphism between
What's an isomorphism?
something that's one. It's a function.
What kind of function?
Bijection.
A bijection that preserves the algebraic structure.
Yeah.
How do you show two topologies are the same? You find a homeomorphism. What's a homeomorphism? A bijection that preserves continuity. Okay, so how do we show that two sets are the same size?
You find a bijection.
You find a bijection! If I can create a bijection from set A to set B, those sets have got to be the same size. Alright?
Yeah.
A bijection is like the simplest structure preserving map that there is. Preserves at least the size of the sets. It might break other structure, but at least preserves the size. Okay, so if I can create a bijection from H to this equivalence class, then they have to be the same size. If I map everything in one class, does that already appeal to your intuition, or do I need to make it click somehow? Still need to make it click?
Yeah.
Okay, let's make it quick. Let's say that there's only girls in here, and there's only boys in that room.
Okay.
And you don't know how many people are in that room. But I tell you, Rhoda, I can map every girl in this room to one and only one boy in that room. Are there the same number of people in both rooms? Yeah. That's a bijection. We map every element in one set to one and only one element in another set. If we can do that, the two sets have to be the same size.
Okay, that makes sense.
Yeah. You say boys and girls, and high school kids get it. All right. So that's all we're trying to do. We got our set of girls here. We got our set of boys here. If I can map every girl to one and only one boy, then we got the same many.
Yeah.
That's all we're doing. The same amount, the same cardinality. The sets are the same size. So, that's what we're doing. So, let f, I need to justify that f is a function here for a second, but I'll justify it here in a second, but stick with me. Let f be a function from h to the equivalence class of g. By f of h is equal to h dot g. Now, there's no reason that you should know that this is a valid function yet. We're going to justify that here in a second. And observe that f of h dot g inverse is what? It's h dot g inverse, right? I said f of h, I'm defining f of h to be h dot g.
Yes.
So f of h dot g inverse is h dot g inverse is h. H is in big H. How do I know little h is in big H? Because my function maps from big H.
Yeah.
F maps from big H. So pick some little h in there. And when we take f of little h and we map it with this, we just get little h out. Little h is in big H. Therefore, f of h is congruent to g mod h. What does it mean for this to be true? It means that this is in H.
Yeah.
You follow that? So what I'm justifying really quick here is that the image of this function is in fact g's equivalence class. So this function is a function from H to g. That's all I'm justifying so far. So I didn't lie to you when I drew the function this way. So this function with this mapping is in fact a function from H to g's equivalence class. Because f of h dot of g is equivalent to g mod h. Or f of h is equivalent to g mod h using this mapping. Have I lost you?
Yeah, why did you do all that?
Okay. I am looking for a function that is a bijection from H to g's equivalence class. That's what I'm looking for.
Okay.
If I can find a function that is a bijection that does that, then these two are the same size, which is what I'm trying to prove.
Yeah.
So I'm saying, first off, I say, let f be a function from H, ignore the 2g part. Let f be a function whose domain is H, and maps little h to h dot g. Right?
Okay.
I'm justifying, from here on out, I'm saying, and notice that if I define f this way, then its image is g's equivalence class. Maybe not all of it, but a subset of it at least. So this function maps h into g's equivalence class. That's what I'm justifying from here on out. So that from line 2 onwards, I can now say that f is a function from h to g's equivalence class, and now I just need to show it's a bijection. So first I'm showing that this is in fact a function from h to g's equivalence class, and then I need to show it's 1-to-1 and onto, and therefore bijection, and therefore they're the same size. So that's how I go from here. So I need to justify that f does in fact map h into g's equivalence class. So I need to show that f of h is in g's equivalence class, or I need to show that f of h is congruent to g mod h. That's what I need to show.
Yeah.
F of h is congruent to g mod h is the same thing as f of h dot g inverse is in h. And f of h dot g inverse is h dot g inverse is just h is in h.
Okay.
So that's true. So this is a function from h to g's equivalence class. So we've got a function from here to here. Next we're going to show, I don't know if we're going to do 1-to-1 or onto first. Looks like we're doing 1-to-1. So next I need to show that this function is 1-to-1. How do you show that a function is 1-to-1?
You show that everything from your left hand set maps to something in your right hand set.
That's a function. That always happens.
If you have the same right hand, then you have to have the same left hand.
Right. F of x equaling f of y implies x equals y. If the outputs are the same, they came from the same input.
Oh, that's right.
In other words, I can't have one output coming from two different inputs. Well, as an example of a function that's not that way, f of x equal to x squared. 4 comes from 2, and 4 comes from negative 2. So this is not 1-to-1. So, let h and h prime be two elements such that their outputs are equal. I need to show that this leads to their h equaling h prime. If f of h equals f of h prime, then h better equal h prime, otherwise we're not 1-to-1. With me?
Yes.
Well, f of h, what is that? That's h dot g. F of h prime, that's h prime dot g prime, or dot g. Here's f of h, here's f of g, or here's f of h prime. Now what do? We dot both sides by the inverse element of g, right? If this is equal, this is equal. And if this is equal, h is equal to h prime. Therefore, f is 1-to-1. Good? Now I need to prove that f is onto. How do you show it's onto? I need to show that for any element in g's equivalence class you choose, I can find an element in h that maps to it. Right?
Yeah.
So, for, I don't know what we want to call it, b be some element in G's equivalence class, comma, and let let me see. Let B be in G's equivalence class. What does that give us? That gives us that B is congruent to G mod H. That gives us that B dot G inverse is in H. Right? Okay. 5. Let H equal B dot G inverse. What does that give us? That gives us that f of H is equal to what? B. You see that?
No.
Let's write out one more step. F of H is equal to, what's H? Maybe write it this way and then it would help. F of H
Oh, now I see it. Yep.
is equal to B.
Yep.
Okay, so notice H, little h is in big H, right? Little h is in big H, and f of little h equals B. So we space out that for any B you choose, I can find a little h in big H such that f of little h maps to your B. Okay? Which gives us on 2. So finally, 6, therefore, they're the same size. Therefore, the size of G is equal to the size of A, not the size of G, sorry. The size of little g's equivalence class. And we're done. So all equivalence classes have the same size. Is there any question about that lemma? Nothing? You know Morse code too? No questions? Alright, so we'll move the camera and now we'll finally do the main theorem of this whole section, which is what we were hinting at before, maybe before I move the camera. Specify what we're going to prove. What we're going to prove is something that we hinted to way back here. We're going to prove that any subgroup you have, anytime you have a subgroup, the size of the subgroup divides the size of the initial group. That's what this whole section is leading up to, and that's what we're going to prove. The size of a subgroup divides the size of the group. Okay? Kind of a roundabout way to do it, huh? And then maybe I'll do one more thing for you before the class is over. Maybe. Let's see. Stay on. Turn it a little. Okay. So let me write down exactly the author's verbiage for the theorem that we're proving. And this is a massive proof, so hopefully one whiteboard's enough. Theorem 42.4. Let H dot be a subgroup of a finite group G dot comma and let A equal the size Okay, so we already have H and G, right? So I won't say let H be a subgroup of G, blah, blah, blah. So, 1, observe that congruence mod H partitions G into some number, we'll call it n, of equivalence classes. Right?
Yeah.
So we can use this relation to partition G up into n equivalence classes. Now, notice that we're using the fact that this group is finite. So this number n is some positive integer, 1 or bigger. With me so far? 2. Then a times n is equal to b, right? A is the size of H. Each equivalence class has that as its size. Every equivalence class is of size H. So every equivalence class is of size A, the same size as H. A is the size of H. Every equivalence class is the same big as H. That's what we just proved over here.
Yeah.
So we have n of them, all of size A. They're a partition of G. G has size B. So when you count all the elements in all the partition classes, you get B, which gives us that A divides B.
What?
You able to follow that one?
You are so.
What?
I was like getting ready for this.
Look at that, you paid attention. If you knew to laugh, you were at least paying attention. That's encouraging.
It's discouraging.
It's discouraging. Oh, I'm sorry, did you want me to make it harder?
I literally wrote it on a whole different paper, but
Just write your thoughts down underneath how things you feel. How happy
I
you
am
were
so
that it
mad
already.
at
You sure smile a lot when you're mad. I hate to see you happy. It's scary. Alright, so that's the end of the section. Let's go on break, and then when you come back, I'll give you a quick proof of what we're going to be covering next week. Next week we're going to be covering Moz Little Theorem. Not Moz Little Theorem, sorry. It's called Moz Little Theorem. It's different from Moz Little Theorem. You know Moz Little Theorem? Definitely. Alright, let's go over really quick what Moz Little Theorem is. Moz Little Theorem, so let's look at numbers. A plus B equals C. Is it possible for you to find 3 numbers that make this true?
yeah.
Do it.
1, 2, 3.
1, 2, 3. Because 1 plus 2 equals 3. Right? What about if I make these squared? Now can you do it?
Yeah.
Do it.
I don't know, like, how to do it. 1, 3, 4, 5.
1,
3, 4, 5.
3, 4, 5. You're telling me 3 squared plus 4 squared equals 5 squared? You're saying 9 plus 16 equals 25?
I don't know.
Yeah.
Yes.
Oh, you do know. Okay, so you were able to do it when I put 2 there. Alright, what about if I put 3 here? Can you do it?
I don't think it.
I'll give Emma a lot of money if she can do it.
Oh, you can't do it.
You can't do it.
Why can't you do it?
So, in general, put n here. For n greater than or equal to 3, there are no solutions. Integer solutions. That is Fermat's last theorem. Fermat was a famous mathematician, and he was a somewhat reclusive, kept himself, and he had developed a bunch of math, but a lot of the math that he had developed wasn't known until he died, and then people went and got his journals and started reading through them and realizing all the amazing things he proved. One of the one of the most famous mathematicians that there are. His name comes up all the time. Him, Euler's, and another one that comes up almost everywhere. Anyways, so in his notebook, in the margin of his notebook, he said that this is true, and he put a note underneath. He has a proof, but it won't fit in the margin. So he didn't put the proof. And we never found his proof. So the big question was, how on earth do you prove this? And it was an open question in mathematics clear up until the 1990s, I believe. I don't know what year, Wiley, something like that, proved it. But not that long ago. So Fermat is someone living in the 1700s, and it took us roughly 200 years to come up with a proof for this. So one of the big questions is, did he actually have a proof? Most mathematicians say, no, he didn't have a proof.
That's so weird. Why did he?
Because the mathematics that they had to use to prove it was not understood in his day.
So he just wrote down something and just guessed.
Yeah, so it's oftenly called Fermat's last conjecture. A conjecture is something that you believe to be true,
I have proof.
but you haven't proven it yet.
I believe in it.
Well, I believe that he thinks he had a proof, but that there was an error in the proof that he didn't know was in there. Because that happens all the time in the mathematics community. Someone thinks that they've proven something, and then other people come along and say, no, actually, it was mistake here. Since he was so reclusive, no one ever saw his proof, let alone challenge it. So that's why it's really famous. And it's one of those things that the question is so easy for you to understand. It's rare that we can talk about something that's really, really, really hard to prove, and yet you can explain it like that. You knew exactly what you were trying to prove here. And it almost feels like if I put that on a test, you feel like, with enough time, maybe I could come up with something. Right? Like, why is that so hard? I should be able to prove
Sure,
that.
Emma thought that.
It's a common, the mathematician who proved this, he was an absolute genius. Something that intrigued him when he was young. He says exactly the same when he came across me. He's like, it can't really be that hard. And he ended up proving it.
How long did it take him?
And a good portion of his life.
That's so sad.
It's not. It's very, it's amazing that he was able to do it. There's actually a Star Trek episode. Which one? Star Trek Next Generation, I think. I can't remember what it is. But the series was being produced in the late 80s, maybe early 90s. And Star Trek happens way in the future, right? And then in one of the episodes, they have the captain of the ship trying to solve this proof. Because in the future, it still hadn't been solved.
Oh my god.
And then so the episode, I don't know if it ends with it, but I think it ends with it, but it probably just has a quote in there. Maybe some things will never be solved, like for Moz last theorem. And so within a few years of them making that episode,
They're like, oh crap.
So what can predict you in the future?
Yeah, there goes that prediction. Anyways, so that is for Moz last theorem. Now for Moz Little Theorem, which we have tons of proofs for, and which can easily be proven, and which we will prove after the break, and then it will be the focus of next week. For Moz Little Theorem is let P be prime and let A be an integer. Let P be prime and let A and Z. Then A to the P is congruent to, so they didn't do the 1. Sorry, I was going to write it wrong. A to the P is congruent to A mod P. That's what we'll prove. Do you understand what this is saying? Back to regular modular arithmetic.
Okay.
A to the P, when you divide it by P, has a remainder of A. What do we mean? I mean 27 to the 17 mod 17 is equal to 27, but mod 17, 10, is equal to 27 mod 17, which is equal to 10.
Oh, okay.
So this is a theorem that is of great practical importance when it comes to working with numbers. Very useful one in number theory. This is a very useful one for computer science, one that we're very interested in, because we're able to find the remainder of a very massive number in a very small amount of time. Because what is 27 to the 17?
How did you get 17 when it's A?
I picked some random integer a,
Yeah, it says
and some random number, prime number 17.
and then you put P instead of A.
27. A to the P, mod P, is equal to, oh,
I'm so confused.
this, it says the exact same thing as this. A to the P mod P is equal to A mod P.
Oh,
Where now we're talking about
so we forgot
the
about
remainder we need to divide.
the other P.
Do you remember that proof? Oh my
You
goodness.
just are leaving out the A.
Left out A?
The A to the P is congruent to A mod P.
A to the P mod P is equal to
What-
A mod P.
what about
Is
the
the same thing as
here?
A to the P is congruent to A mod P. These are logically equivalent. You proved this.
Oh.
That was on your homework. That was on your test. This was one that I made sure that you got very comfortable in. I also did it in class because that's one that comes up so much that needs to become second nature to you. When you see this, you can think about it this way, or you can think about it this way, and it almost makes no difference. And here's how that helps us. 27 to 17 has an absolutely massive number. What's its remainder when you divide it by 17? How am I supposed to know that? Well, it's 10.
That's
Because 27 to the 17 mod 17 is the same thing as 27 to mod 17. And 27 mod 17,
Oh.
that's real easy. So instead of working with A to the P mod P, I can just work with A mod P.
okay. I see.
Now you see it. It also helps us in ways even if this wasn't a prime number, but we were still dividing by a prime number. Because if I would have had this A to the 18 mod 17, well, that's the same thing as 27 to the 17 times 27 mod 17, right?
Yeah.
And now I know what 27 to the 17 mod 17 is, and now I just need to figure out what 27 is. So this is going to be, that's going to give me, well, it's going to be now the same thing as 27 squared mod 17, right? Because this is the same thing as just 27, and then here's another 27, so that gives me 27 squared. What's 27 mod 17? That's 10, so this is going to give me 100 mod 17. And now that's very workable, right? What's going to be? What's 5 times 17? That's going to be, what?
85.
85, thank you. So, the remainder is
50.
50. So there we go, some massive number, and we found its remainder when you divide by 17 relatively easily. So that's why it's so useful. Helps us find remainders for massive numbers really quick when you're doing division. So we'll go on break. That's the end of new material. We'll go on break. When you come back, I'll do one proof that I really like from a different textbook for proving this. And then next week we'll prove it again the way the book does. So this will be the end for lecture material, and then the proof that I do will just be for fun. And I don't think we need to record it because you'll have next week's recorded, but you have it in the book.